We will introduce today a new chapter. This chapter will go over dimensions, tolerances, and surfaces. We'll see what are the processes that can be done for a surface finish, how we define dimensions, what are tolerances that are allowed in manufacturing processes. Mainly, manufacturing processes differ a lot by the tolerances they allow. So in some cases, if you have an application that doesn't require an extreme accuracy, it will be much easier to have your product than if you want to produce, let's say, a very smooth surface, perfectly finished. So higher the accuracy you want to reach, more complex will be the manufacturing process you should undergo. And sometimes you should do a series of manufacturing processes to reach the final output you want. We'll also introduce conventional measuring instruments and gauges. You should go over these in the manufacturing lab in detail, but I will try as much as possible to make you familiar with these tools. I will post on the YouTube playlist some videos showing you these instruments and how we can use them in labs. We'll also talk about surfaces, as we already said, the finish of a surface, how we can alter its roughness, etc. And we'll see what are the measurement tools that can be used to assess surface properties. And finally, we'll see the effect of this on manufacturing processes. Okay. So this is in brief, the outline we'll go over. So to start with, we will start with dimensions and tolerances. There are factors that determine the performance of a manufactured product other than the mechanical and physical properties. So, and this will include dimensions. And when we talk about dimensions, we have several types. We have linear or angular dimensions. So we'll have different tools to measure linear and angular sizes of a certain component specified on the part drawing. Always on the drawing, you have ideal product, ideal dimensions. But you will never be able to exactly produce by manufacturing the same size without any error. You will always have an error. And as we already said, depending on your application, the error can be variable. So in certain applications, you can allow larger errors than others. And lower the error you want to reach, higher the accuracy then, and more complex will be the series of manufacturing processes required to reach your objective. Now, when we talk about tolerances, they consist on the allowable variations from the specified part dimensions that are permitted in manufacturing. And we'll see that we have several types of tolerances. Sometimes we can allow a change in dimension from one side only. So for example, let's say you have a certain part, let's say like this. You want to produce a cylinder of diameter equal to 20 centimeters, let's say. You can say, for my application, I can allow little bit larger diameters, but I cannot allow lower. So in this case, we say that the tolerance is from one side, not from both sides. Okay. So to start with, we will start with the definition of dimension. A dimension is a numerical value expressed in appropriate units of measure and indicated on a drawing and in other documents along with lines, symbols, and notes to define the size or geometric characteristic or both of a part or part feature. So when we mean, what do we mean by this? So for dimension, you can invent any dimension you want. You can create it. Okay, so let's say now we are mainly familiar in SI units with meters, in English units with feet. You can come up with a new dimension, but just you should define it and say, let's say 1 unit of my dimension will represent what? And then you can use the following scale for any application. Okay, of course, the most used one are the SI and English unit systems. And these are related. We can convert from meter to feet We can convert also in English system, we have feet and inch. So all of these dimensions, all of these are dimensions. So 1 inch constitute a dimension, 1 feet a dimension, 1 meter another one, but they are specified such that in a way now if I tell you 3 meters, you directly imagine how will be your length. So these are international dimensions that we are using. The dimension indicates the part size desired by the designer if the part could be made with no errors or variations in the fabrication process. And as we said, this is not possible. We'll always have an error, but if the maximum, we can minimize this error, the more accurate will be our manufacturing process. Now, concerning tolerances, as we said, a tolerance is the total amount by which a specific dimension is permitted to vary. And we have several types of tolerances that we'll define now. And the tolerance constitutes the difference between the maximum and the minimum limits we can allow. So going back to our example that we want to manufacture a cylinder, we can specify, let's say we specified that we wanted to have a diameter of 20 centimeters. You can say, I can allow diameters between 19.5 to 20.5 centimeters. So in this case, you allow tolerance in both directions. You can go below 20, you can go higher than 20, and your error, your maximum error then will be here, because here it's symmetrical. Sometimes you can have tolerances that are not symmetrical. So if you impose, for example, I can allow between 19.7 and 20.5. So you can go 0.3 centimeter below your desired length, and you can go plus 0.5 centimeter above the desired one. So this will define if you want the minimum and maximum dimensions allowed. Now, variations will occur in any manufacturing process, but always for any manufacturing process, we should determine what are the tolerances, because it depends on our application and what is the desired tolerances we want. We can select the appropriate manufacturing process. And tolerances will be used to define the limits of the allowed variations. And now we'll see that we have different types of tolerances. So to start with, okay, as we said, we can have different types. The first one is the bilateral tolerance. When we talk about bilateral tolerance, this means that we can go beyond, or we can go below the value desired. So here, for example, let's say we want to design a cylindrical part of the following diameter. We can go plus 0.005 or minus 0.005 of the desired value. Now, in case sometimes if we can have a bilateral tolerance that is symmetrical, and also it can be unbalanced. Okay, so the variation is permitted in both positive and negative direction from the nominal dimension in bilateral tolerance. It can be a balanced tolerance or an unbalanced bilateral tolerance. When we talk about unbalanced tolerance, this means that the positive value or negative value are different. They don't have to be symmetrical. Okay. Now, another type is unilateral tolerance. So as we said, in some applications, we can only allow tolerance from one side. And of course, this will be more critical. And we'll see how, we'll make sure that the manufacturing process will be designed in a way to only allow a tolerance from one side and not from the other. So here, for example, when we talk about unilateral tolerance, it can be, the unilateral tolerance can be from the positive or negative side, but not both. Okay, so here, for example, you can say, I can allow larger diameters, but not lower ones. Or you can say, I can allow smaller sizes, but not larger ones. So you can have plus 0 and minus 0. Let's say 0.005, for example. Okay, so in this case, we say that variation from the specified dimension is only permitted in one direction, and it can take place in the positive or negative sides, but not both. Now, when we talk about the limit dimensions, they represent the minimum and maximum dimensions allowable. So we can calculate them if we know the nominal value. The nominal value represents the value that we desire. So here, for example, we can say the nominal value is equal to the desired length is 2.5. Okay, and whenever you know your tolerance, you can determine the maximum and minimum dimensions allowed. So here, if I tell you the nominal is 2.5 and the tolerance is plus or minus 0.005, you can directly determine the maximum and minimum dimensions allowed. So the maximum one will be 2.5 plus 0.005. And the minimum one will be 2.5 minus 0.005. Now, concerning measurement, we have different tools used for measurement. As I told you, to be more familiar with these tools, I will post for you on the YouTube playlist several YouTube videos that will help you to see how we use these tools in labs. So measurement is simply the procedure in which an unknown quantity is compared to a known standard one using an accepted and consistent system of units. Measurement will provide a numerical value of the quantity of interest within certain limits of accuracy and precision. Even our measurement tools, of course, are not have a certain error. And depending higher the accuracy of these tools, higher will be their costs. So we'll see here that you have, for example, for very advanced manufacturing processes where the error cannot be very large, you need to have a very small error. You cannot use conventional tools that we use in labs. You need to have a much sophisticated equipment that is very well prepared to lead to a very small error of measurements. And we can see here that higher the accuracy, higher will be the cost of these measurement devices. Now, in order to determine the error, we can talk about two criteria, which are accuracy and precision. So, and there is a big difference between both. Of course, in any measurement tool, we need to have both. It should be accurate and it should be characterized by high precision. When we talk about accuracy, it means the degree to which a measured value agrees with the true value of the quantity of interest. So the accuracy will see the difference between the true value, the exact value, and the one that is measured. So, of course, a measurement procedure should be accurate. And it will be accurate when it will avoid systematic errors in the positive or negative sides. Now, when we talk about precision, precision means the degree of repeatability of the measurement process. You know that whenever you do an experimental procedure, you don't do it once. You take several measurements because you know that I might have experimental errors. I might have, for example, any defect in the experiment might lead to difference in results. So to make sure that my points are satisfy precision, I should repeat the experiment several times. And in case I have one point deviating from others, I can eliminate it from data points. So good precision will mean that random errors in the measurement procedure are minimized. Now, of course, we need to ensure both accuracy and precision in our measurements. So this is a small figure showing you the difference between accuracy and precision. Okay. So for example, when you are playing here, what you want to do is to reach your goal. Your goal is to reach this point. Okay. So when we talk about accuracy, accuracy will represent the variation between your goal and if you want the point you will reach on the set. So to say that you have a high accuracy, all your points should be close to the goal. Okay. So for example, in this figure, you have high accuracy. In this one, no, you don't have high accuracy because all your points are far from your goal. But you can say that here you have a high precision. because you are always reaching the same, nearly the same location. So your result is repetitive. So if you do it several times, you are always reaching same location. So this is a high precision but low accuracy case. However, here you are having high accuracy because all of your points are close to your goal, and at the same time you are having high precision because your points are all nearly at same location. In this case, for example, this is what we call high accuracy but low precision. It's true that you are around your goal, so you can consider that it's accurate, but it's low precision because you are not reaching same locations. So you are having random locations around your goal. And finally, here you have low accuracy and low precision because you are far from your goal, and at the same time you have random locations. You don't have repetition of your result. And both are desired in any measurement. We should have both accuracy and precision to consider that we are having good measurements. Now, we'll start to go over the conventional measuring instruments and gauges. So now we'll talk about them in theory. And please, if you can go over the videos, they will be helpful for you. I will post a series of videos for you to see how we use and practice these conventional measuring instruments. So to start with, we have the precision gauge blocks. It's important to know that we have two types of measurement devices. Some devices are graduated, so you have graduation on them. You can directly read the value, and others will just be as comparison tools. They will not be graduated, but they will help you to compare dimensions. We'll see how. Okay, so now the conventional measuring instruments include pressure gauge blocks, measuring instruments for linear dimensions. We have comparative instruments. So these ones in general are not graduated. They are used for comparative purposes. You have fixed gauges and angular measurements. So to start with, the first type is precision gauge blocks. They are standards against which other dimensional measuring instruments and gauges are compared. So if you have very high accuracy of precision blocks, you will have a very high cost, and they will be used, if you want, as a reference. And when we manufacture them, we'll use most advanced manufacturing processes tools, so to minimize any possible error. And then we'll use them to be, if you want, compared against other measuring instruments. So you can check the accuracy of measuring instruments using these gauge blocks. Okay. Now, in general, these blocks are usually of square or rectangular shape, and their surfaces are finished to be dimensionally very accurate and parallel to the plus or minus several millionths of an inch. So you imagine that you are dividing an inch by a million parts. So this will give you really very accurate gauge blocks. Okay, so when you look at them, they are nearly polished to a mirror finish. So it seems for you that they are perfectly smooth. Now, precision gauge blocks are available in certain standard sizes or in sets containing a variety of different sized blocks. So this is, for example, a set of gauge blocks, and we already said that they are accurate to plus or minus several millionths of an inch. Even here, okay, depending, you have different sets depending on this accuracy. So when we talk about several millions, we can go to several categories. And the more you divide, so the more you have accurate device, then you can reach smaller and smaller dimensions. So this is why when you go to the market, you have different prices of these sets. And the higher the accuracy, higher will be the cost. So as you can see, they are designed in blocks of different dimensions. So for example, they tell you here you can read on the set, you can read, for example, this block stand for which dimension. Okay, and to make sure they can be used to test, if you want, the precision of a certain measurement device. You can bring a measurement device and measure with it this dimension. The device will not be able to give you accurately the same value here because of the error involved. So using these blocks will allow you to determine what is the error of your measuring devices. Now, we have, as we said, for measuring tools, we have linear dimensions and angular dimensions. We'll start with tools used for measurement of linear dimensions. And these tools will be divided into two types. The first one is graduated measuring devices, which will include a set of markings. So, for example, your rule, the normal rule that you use in math or in physics to have your graphs, is a graduated measuring device. And it will include a set of markings or on a linear or angular scale to which the object's feature of interest can be compared for measurements. However, when we talk about non-graduated measurement devices, they will not have a scale on them, and they are just used to compare dimensions or to transfer a dimension for measurement by a graduated device. So for example, we'll see some tools that are not graduated, but they are helpful to set a certain dimension. So for example, you want to measure, let's say, the diameter of a sphere. You come up with a tool, you just put it on it, you determine from your tool what is the distance between these 2 points, but you cannot read the value on this tool because it's not graduated. Then you transfer it, okay? So you take this tool and then you go to a measurement device that is graduated and you measure then what is this distance. You might tell me why to do this, why to not directly measure it with a graduated device, because we'll see that some dimensions like the diameter of a sphere are not easy to measure accurately with if you just put a rule here, you cannot really track the diameter. You will always have an error. So the other tools will be able to really, by their design and geometry, will be able to exactly place, if you want, the diameter, and then you can measure it with a graduate device. This is called a transfer of dimensions. So you will compare the dimension of a non-graduate measuring device with the measurement of a graduated device. So for example, okay, this is an external micrometer. We'll see together in detail how we use such devices. If you observe the scales here, you have several scales, and having several scales will help you to increase the accuracy of your measurement device. We are just familiar with the common rule which we are using, which is very simple. We already have a scale divided into one scale, okay, divided into, so for example, the conventional rule we can read, the minimum dimension we can read is 1 millimeter, okay, while here the 1 millimeter is divided into several parts. It can be divided into 10, 100, it depends on the accuracy of your second scale, okay? And we'll see how to read such measurements and how vernier scales will be helpful to have better accuracy in measurements. So this is what we call vernier caliper. Okay, I will not talk now about the scales because it's a little bit challenging. So in class, we'll do several examples to understand how we use these different scales, how we read them. Okay, but just you should know that whenever you have a vernier scale, we can reach a higher accuracy, because in this way we can divide the dimension, the basic dimension here. And for example, here, let's say the basic dimension is 1 millimeter. This 1 millimeter will also be divided into many parts. So here, for example, you have 1/20. We divide it into 20 parts. You have scales that can divide into 100 parts or into 10 parts. It depends on the precision of the vernier scale we are using. Now, one example of non-graduated tools is calipers. So here, for example, you can see it already. So you have its geometry is designed in a way that it can easily handle objects like spheres, okay? And it's not graduated. So just you will use it, for example, to measure a certain, to have a certain dimension and transfer it to a graduated equipment and read it. Now, we have also what we call mechanical gauges, and they are based on dial indicators. So mechanical gauges will be designed to mechanically magnify the deviation to permit observation. Sometimes you are measuring very, very small dimensions, and you cannot see them in a normal case on a scale because they are very small. This is why, in order to read these small dimensions, what we can do, we can use an equipment that will magnify these dimensions, and the scale is designed in a way to have appropriate reading of the measurement. Okay, we use a lot in this case, if you want angular measurements, as we'll see. Okay, so you can have a needle that will do rotation, and this rotation will be depending on the value you are reading. So the most common instrument in this category is the dial indicator, which will convert and amplifies the linear motion of a contact pointer into rotation of a dial. Now we'll see it in an example in the slide coming after. So the dial will be graduated in small units, such as 0.01 millimeter or 0.001 inch. And these devices are widely used to measure straightness, flatness, to make sure that we have a good parallelism in surfaces, squareness if you want to test that if we have shapes as really square, so we can go over the side and make sure that we don't have deviation from a lot of deviation from the nominal size. We can test also roundness and runout. So for example, we'll take an example now. So this is a dial indicator. Okay, the idea is that you will pass this point. So let's say, for example, you want to check the flatness of a surface. You have a surface and you want it to be flat as much as possible. So this is your surface. If you want to make sure that it's really flat and you don't have high roughness on it, okay, so it's perfectly smooth and flat, what you can do is you can pass by this pointer over this surface, and any deviation from the required value here will lead to a rotation of your dial. And you can read maximum deviation from the nominal size in the positive or negative directions, okay? And then this will allow you to determine the degree of flatness or smoothness of your surface, okay? So for example, here, another application, we can test if you want, if the diameter of a cylinder is really uniform. And of course, we'll have some deviations, but better the finishing, you will have smaller deviations between the nominal size that you want and the actual diameters across your section. So here, for example, to make sure of the uniformity of your diameter for this cylinder, what you can do, you can rotate, and you can do it in two ways here. You can make sure of your diameter for a certain circular cross section, and also you can make sure of, if you want, if it's varying with position by moving this pointer in this direction. So first you can move it, you can move your pointer around the surface to make sure that the distance from the center is nearly uniform, so the manufacturing process is accurate. And also you can move your pointer along this direction to make sure that if I take different sections, I will not have different, I will have very close diameters, so the error is relatively small. So here what will happen, as your cylinder rotates, okay, is this pointer will move to remain in contact with it, and the motion of your pointer, okay, will be transformed through a transducer to an electrical signal, and this electrical signal will be transformed to the motion of a dial indicator that will tell you how much you are deviating from the nominal size. Now, you know that with advance of technology, we are trying to move from mechanical devices to electronic devices, because the electronic devices are characterized by larger accuracy, and also they have very fast response. Okay, so electronic gauges are family of measuring and gauging instruments based on transducers that are capable of converting a linear displacement into an electrical signal. Electrical signal will be amplified and transformed into a convenient data format, such that as a digital readout. So for example, you can or transform it into, as we have seen before, into dial motion, or the better will be to have a digital readout. So you can have, all you have to do is to read the final value. You don't have to make any effort. And this will also reduce the error of the reading error. But of course, such equipments have a very large cost, and they will be used in developed labs, which requires high finishing manufacturing processes. Now, applications of electronic gauges have grown rapidly in recent years because of advance of microprocessor technology, and they are gradually replacing many of the conventional devices we're used to use. So these are electronic gauges. So here, in this case, you don't have to do your own reading. You can just read the final digital answer. While in the Vernier scales I have shown you before, you should know how to read it, and it has a certain technique to read the dimension. Here, since it's digital, so you don't have to do any effort. You just take the value that you observe here. Now, another type of gauges that are also used are go, no-go gauges. And they are named in this way because one gauge limit will allow the part to be inserted, while the other limit will not. So the idea is that when you design a go, no-go gauge, the difference in dimension between the go and no-go one is really very, very small. This will allow you to trap a certain dimension in a very narrow range. Okay, now we'll take several examples. So for example, if you consider, again, if we have a sphere and we want to measure its diameter, okay, you have specific tools designed in a way that have circular shapes. And then you can take your sphere and try to insert it in this go, no-go gauge, okay? Whenever you reach, whenever you have a size very close to the actual size of your sphere, you will have the go gauge will allow it to be inserted, while the no gauge will be a little bit smaller in dimension and will not allow the sphere to be inserted. Then you can trap that the dimension of your sphere will be lying between these two. Okay, so you can say that the maximum size, for example, here's the maximum diameter of the sphere is equal to the go gauge size. However, and we are sure that this diameter is larger than the diameter of the no-go gauge. So you can limit a lot, and you can trap your dimension in a very narrow range. Okay. Now we say that the go limit is used to check the dimension at its maximum material condition. What do we mean by this? So as I told you here, if you have a sphere, and it can pass through a go gauge, but not through the no-go gauge. So you can say that the maximum diameter of the sphere is equal to the size of the go gauge. So when we talk about the maximum diameter of a sphere, then this corresponds to the maximum material condition. So this is the maximum material we can have within the sphere. Okay. However, if we are measuring, if you want a hole, okay. So let's say we have another application, and we want to measure a hole. Okay. If you want to measure the hole, then what will happen is that the go gauge will be able to pass through your hole, but the no gauge will not be able to pass by. And then in this case, the no go gauge will have a diameter larger than your hole, okay, while the go gauge is the minimum diameter of your hole. So then you can say when I measure a hole, the go gauge will give me the minimum diameter of my hole, okay? And minimum hole diameter also correspond to more material, because if you minimize the hole size, then you maximize the material. This is why we say that the go limit maximize the material condition, okay? If it's measuring an external feature, okay, it will give you the maximum size of it. While if it's measuring an internal feature such as a hole, it will give you the minimum size of it. So in both cases, it will lead to what we call maximum material condition. So pay attention for this idea, okay? Now, for the no-go limit, it will be used to inspect, in opposition to the go limit, it will inspect the minimum material condition of a certain dimension in question. Okay, so I repeat the idea. It's the maximum material condition because when it's measuring in external size, it will give you the larger limit. So this will correspond to more material